So what do these models do? What do the models that we have do? Well, they are actually mathematical formulae which allow us to calculate the shear stress at any shear rate we wish by applying a function f. Now, expressing that mathematically, we can determine the shear stress, which is tau, by applying a mathematical function to the shear rate, which is gamma. So what all these models can be broken down to this equation. That's something to bear in mind. You apply a function to your shear rate, and you can determine what your shear stress will be at that shear rate. Now, the parameters of this function f depend on the selected fluid model. For a Newtonian fluid model, f is actually mu, as I showed you earlier on the graph. F becomes mu, so that's basically tau equals viscosity times shear rate. For the Bingham plastic fluid model, F is actually PV and YP. I will show you these models, the actual equations for them in a minute. But the function that we apply to the shear rate is actually a combination of PV and YP, which are two mud parameters that are measured. For the power law fluid model, for a power law fluid, we would apply a function which was based on the parameters n and k. I'll explain these again in a minute as well. And for the Herschel-Bulkley, or the modified power law, yield power law, whatever you want to call it, for that model, we've actually got a tau 0 and an n and a k value. There's three variables in there. But all of the models can be reduced to this. Tau equals f times gamma. And the f is basically a combination of some of these parameters here, some of these variables there. So before I launch into some equations, what I'll actually do is show you graphically how these models actually describe fluids. Here's where the Bingham plastic law actually lies on a graph. It's a straight line intersecting the y-axis and carrying on up this way. The Newtonian fluid was a straight line intersecting the origin down here and coming up here. And the viscosity determines the slope of that line. The power law fluid intersects the origin and then curves up and becomes almost a straight line up here. And the Herschel-Bulkley fluid starts off somewhere up the y-axis and curves up and becomes almost a straight line again as you get to higher shear rates. So how does that actually relate? How would we relate this graph to an oil well? Well, if we actually have a look at this, shear stress and shear rate, we've got the same four curves on here: Bingham plastic, Herschel-Bulkley, power law, Newtonian fluid. Down at the lower shear rates, we could say this is representative of annular flow. So each of these models are representing annular flow behavior based on these lines. And beyond this point, in the upper shear rates, this would be pipe flow. So all the models are actually approximating pipe flow with the lines that we've drawn here beyond this line here. So at low shear rates, we're talking annular flow. At higher shear rates, we're talking pipe flow. Now, what do I mean by low shear rates? Well, somewhere between 0 and 20 is a pretty low shear rate. Anything above 20 is getting towards the sort of shear rate that you would begin to see in pipe. The shear rate obviously depends on how fast you're pumping. But a low shear rate is below 20. Okay, so your annular hydraulics are pretty much in the range 0 to 20, maybe a little bit higher than that. But then if you're looking at things like hole cleaning, it can be described by this sort of range here. Shear rate in per second, by the way. So it's 5 per second, 10 per second, 15 and 20 per second. That relates to your RPM readings on your fan rheometer of 3 and 6. So your 3 and 6 RPM readings, your theta 3 and your theta 6 would describe your annular hydraulics. And the hole cleaning is described pretty much across the board from down here, sort of 2.5 up to 20. Slip velocity of cuttings is somewhere from the lower range of the hole cleaning line here to somewhere up around about 15. That's your cutting slip velocity is described by the shear rates and shear stresses. The cutting slip velocity actually occurs at these lower shear rates there, that sort of shear rate range. And the rate at which barite sags is less than 5, it's somewhere down here. But the ones that we're interested in are pretty much your cutting slip velocity and hole cleaning for the purposes of this course. So obviously, if you can model flow correctly or well in this low shear rate range, then you've got a pretty good model. If you can't, then it's a pretty inaccurate model for hole cleaning and slip velocity. So now we know that annular hydraulics are determined by the fluid behavior at low shear rates. We actually need a model. We actually need a model which is accurate at these rates to allow us to plan for hole cleaning and cuttings transport, allowing us to drill a well successfully. So we'll now examine each of the models that we currently have access to in our software, and we'll discuss their relative abilities in that area, in the low annular flow area.